Alright, this is section 7.1, and we're going to be talking about voltage and capacitance. So our equations for voltage. So voltage is the potential difference. It's how much a charge wants to move independent of how much charge is there. So our voltage at a distance away from a point charge is going to be kq over the distance from the charge. And that distance is not squared in this equation. Other equation for voltage is equal to the potential energy divided by the charge, and then the change in voltage from one point to another is equal to negative times the electric field times the distance from one point to the other. Remember, a capacitance, or a capacitor, is two plates that end up being charged because they're hooked up to a battery. Our equations for capacitance, to find the capacitance on a capacitor, C is equal to something called epsilon naught, so the permissivity of free space, and that's a constant, times the area of one of the plates over the distance between the plates. We also have capacitance equations in terms of how much energy is stored in a capacitor. So we have electric potential energy on a capacitor is equal to 1/2 the charge on the plates of the capacitor, since that we use capital Q for that, times V. It also equals 1/2 the capacitance times the voltage squared. And it also equals 1/2 charge squared over the capacitance. And then our last equation for capacitance is just capacitance equals charge over voltage. And then remember that V is equal to voltage. That's measured in volts. And C is equal to capacitance. And that's measured in something called farads. And a farad is a large amount of capacitance, so usually we're going to have very small capacitances when we find them in problems. So number 1 says, a uniform electric field with magnitude 5.4 times 10 to the negative second, so 540 newtons per coulomb, is directed parallel to the positive x-axis. If the potential at 8.9 meters is 4.1 times 10 to the third volts, what is the potential at 4.9 meters? Alright, so this is problem number 1. So our electric field is pointing to the right along the positive x-axis, and when we're moving from 8.9 meters to 4.9 meters. So what we have here, we have our electric field. Make the equal sign a little better. We have the electric field equals 540 newtons per coulomb. We have the distance we're moving. It's going to be from our final position is 4.9 minus 8.9. The distance we're moving is negative 4.0 meters. And we also know that our initial voltage is 4,100 volts. So the equation we're going to use is delta V equals negative ED. So we get delta V is VF minus VO equals negative ED. VF is what we're looking for, minus 4100 volts equals negative times 540 newtons per coulomb times negative 4.0 meters. And again, the reason that's negative is, one, we're talking about the x-axis, so we have points to measure from, but also because it's going the opposite way of the electric field. So we'd have to make either the electric field or the distance negative, even if it wasn't along the x-axis. So when we do that math, we get our final voltage, which is what we're looking for, is equal to 6,260 volts. Our next problem, number 2. 2 says, what is the electric potential at a distance of 0.48 meters from a point charge of 6.8 microcoulombs? Then it gives us the value for K. So we have our distance from the charge is equal to 0.48 meters, and we have the charge is equal to 6.8 microcoulombs, is equal to 6.8 times 10 to the negative 6 coulombs. So for this one, we're looking for the voltage. So we're going to use voltage equals K, Q for the distance. So we get 9 times 10 to the 9th for K times 6.8 times 10 to the negative 6 coulombs, and that's over 0.48 meters. And make sure you notice that D is not squared in this equation. When we do that math, we get 1.28 times 10 to the 5th volts. Now we'll do problem number 3. Problem number 3 says 30 joules of work are done to push a 0.1 coulomb charge from point A to point B in an electric field. What is the voltage difference between point A and point B? So we're going to use here, we have the work done is going to equal to the potential energy electric gained. That equals 30 joules. And we have our charge is equal to 0.1 coulombs. And we're looking for our voltage. So the equation we're going to use for this, or the change in voltage, so the equation we're going to use for this is voltage equals potential energy over charge. In this case, we've got 30 joules divided by 0.1 coulombs, and our voltage is 300 volts. So that's our answer for number 3. Alright, let's move on to number 4 is a capacitance problem. It says, what is the capacitance of a parallel plate capacitor made of 2 square aluminum plates that are 4.6 centimeters in length on each side and are separated by 8.1 millimeters? And it gives us the permissivity of free space is 8.55 times 10 to the negative 12th. That's something I forgot to define at the very beginning, so we'll do that now. So that permissivity of free space is 8.85 times 10 to the negative 12th, and that is a constant. So our equation for the capacitance of 2 parallel plate capacitors is C equals epsilon naught times the area of the plates times the distance between them. So what we have in this problem is we have the length of each side is equal to 4.6 centimeters, and that equals 0.046 meters. So we can find our area equals our length squared, so it equals 0.046 meters, 1d squared, and that equals 0.021 meters squared. And then we have our distance between the plates is equal to 8.1 millimeters. That equals 0.021 0.081 meters. So I'm going to substitute into our equation here. So we've got C equals 8.85 times 10 to the negative 12th times our area, so 0.021 meters squared, divided by the distance between them, which is 0.0081. There's another, I made a mistake up here, guys. This should be equal to 0.0021 meters squared. Let's fix this one. There we go. And that's over 0.0081 meters. When we do that math, we get our capacitance equals 2.29 times 10 to the negative 12th farads. Last problem we'll do together is number 5. 5 says a capacitor stores 4.6 times 10 to the negative 6 joules of energy when it's connected to a 3.6 volt battery. What is the capacitance of the capacitor in microfarads? Alright, so what we're going to do, we have our electric potential energy equals 4.6 times 10 to the negative 6th joules. Our voltage equals 3.6 volts. And we're looking for our capacitance. So the equation we're going to use is electric potential energy equals 1/2 CV squared. In this case we have 4.6 times 10 to the negative 6th joules equals 1/2 times C times 3.6 volts quantity squared. We do that math, we get C equals 7.1 times 10 to the negative 7th farads. And if we convert that to microfarads, we divide by 10 to the negative 6th. We get 7.1 times 10 to the negative 1st microfarads. Yeah, microfarads. And that's the end of those 5 problems. Do the last 5 on your own.